I'm very pleased to be chairing this session on Bayesian methods for T&E. We've got a great lineup for you today. Three speakers, two of which will be tutorials, which will be a methods talk. So a little different than the other sessions, but I think we've got a lot of great information for you today. I will first try to get off stage as quickly as I can. I'm just going to introduce our first speaker, Justin Cremidas. He is a research assistant professor at the Intelligence Systems Division of Virginia Tech National Security Institute and an affiliate research assistant professor in the Virginia Tech Department of Mathematics. His research is in the development of theoretical and computational frameworks for Bayesian inference, particularly in high-dimensional regimes. And he has a lot of interests and a lot of applications to that. Dr. Cremidas holds a Ph.D. in mathematics, as well as a master's and a BS in physics, all of which are from Virginia Tech. And he will be giving our first tutorial on Bayesian methods for integrated testing. So please join me in welcoming our first speaker.
Yeah, okay. Everybody can hear me okay? All right, great. So I'm going to try to provide kind of the background, the Bayesian concepts, if you will, and why we think Bayesian methods might be promising for integrated test and evaluation. And then I'll turn it over to Adam, who's going to be talk you through an example application. So, okay, what's the big idea with Bayesian methods? So what we're going to do is typically with T&E, there's an unknown that we're trying to estimate, right? There's some parameter of the system that we're trying to estimate from the test results. And we're going to treat that and the data as statistical quantities, okay? So each one of them will be a random variable, will have probability distributions. And in particular, we're going to try to incorporate all information, including what we know before we collect any data, into our estimate of those parameters. Okay, and maybe what's key is we're going to write down those assumptions very formally and build them into the Bayesian framework. And then so we have this understanding before we collect any data, and then we will update that understanding as data comes in. Okay, so that's kind of the overarching idea behind Bayesian inference. Okay, so I'm just going to talk you through kind of the key concepts of Bayes. So the big idea really is Bayes' theorem, which goes back to Thomas Bayes in the 1700s, and it really looks like this. So here, theta throughout this talk, theta will be the thing that we are trying to estimate. So that's the parameter that we're trying to estimate, and y will be the data. And so we are trying to, as I said, everything will be statistical. So we're trying to estimate the probability of a given value of theta given the value of the data y, right? So it's a conditional probability. And Bayes' theorem says that, let's see, can I point with this? Maybe not. Is that is proportional to, or well, actually equal rather, the probability of the data given the parameter value times some understanding of the parameter value, the probability of the parameter value, divided by the probability of the data. Okay, and there's nothing really mysterious about this. It's basically just if you write down the definition of conditional probability, right, you can write it. You can write this intersection two different ways and make them equal to each other. Okay. In practice, calculating that denominator from the previous slide, the probability of the data, is really hard because it requires kind of thinking through, well, all of the potential values of the parameter, and then all of the potential ways that you could get that data. But we don't really, note that the denominator doesn't depend on theta, right? So it's just a normalizing constant. So we don't typically worry about it, right? We're just worried about relative probability across values of theta. And so we typically just write this proportionality. Okay. And then so these are kind of the three components of Bayesian inference, and each one has a special name. So first, the probability of theta is known as the prior. So this is when I was saying we're going to build in all of our understanding of the parameter before we take any data. That's going to be baked into what's called the prior. Okay. And then we collect data, right? And for a given value of theta, we can say what the probability of getting that data is from some statistical model. And we're going to call that the likelihood. Okay? And then we multiply those things together, and up to proportionality constant, we get what's known as the posterior, which is the thing we're going to try to estimate. Okay? So I'll talk about each of these three pieces bit by bit. Okay, so as I said, the prior is sort of where we're going to encode information that we know about the parameter before we start trying to estimate it. Okay, so you can imagine a lot of ways that you might sort of build a prior, right? Lots of sources of information. And you know, maybe I should start with one that's not even in here. There are a lot of times we know that a parameter of our model lives in a certain domain, right? Like there are many statistical parameters that must be positive, just for example, right? So we might encode that type of information into our parameter, into our prior, right? So that'll sort of dictate that you know, that the model can't try to like give probability to values that we know are not physically relevant, right? But we can also, from a testing perspective, right? We can use previous data, right? So that could come from previous similar systems, right? If this system that we're testing is similar to ones that have been tested before, we might be able to use similar systems to sort of build some understanding. We can use simulation data potentially, or previous phases of tests. Like if we're in you know, later phases in OT, for example, we might be able to use DT to build our prior, right? Theory. So like, you know, sometimes maybe you don't want your model to violate physical laws, so you may be able to say things from theory about that, or you know, potentially subject matter expertise. If you have a SME who just knows certain things about what likely values of this parameter are, it might be worth encoding that into the prior. Okay. Yeah, so that's the prior. The likelihood is where all of the data comes into Bayesian inference. So this is similar in a way to what you might sort of encounter in frequentist methods. I sometimes like to think, like I often work in problems where you can sort of think of there being a model mapping your parameter space, maybe a physical model, maybe a statistical model, mapping your parameter to the data space, maybe with some error in the measurement, right? And if you have sort of a simple model like this, you can write down, you know, where here I'm just assuming the error is normally distributed. You can write down what the likelihood is, which is just the probability that this error is taking you from the output of the forward model to the data. Okay, so this likelihood might be very narrow if your sensors are good, or there's less noise in the measurement, or wide if the measurement's more noisy, for example. Okay. So the key is that this will be higher for values of theta that match the data well, and lower for values of theta that do not match the data well. Okay. All right, and then as we said, the posterior is proportional to the product of the likelihood and the prior. And the idea is that this thing will be high when for values of theta that match our prior knowledge and the data well, right? So this will be, it's a probability distribution that is, it'll be highest for if there are values of theta that match both well. It will be lower if it does not match one well, right? And it'll be very low if it does not match either, sort of our prior understanding and the data well. Okay, and this is the answer in the Bayesian setting, right? So this is what we are going to get out of Bayesian inference is a probability distribution on the parameter that we want to try to estimate. Okay. And yeah, so really the idea is if our data or our prior hasn't told us much, this may not be a very narrow distribution, right? We may not have learned all that much. But if the data or the prior are telling us a lot, this may very well be a very good estimate of theta, right? Okay, so those are the three sort of components, three terminology you should know if you're learning about Bayes. I want to backtrack to the priors briefly because a lot of people get worried about this. Will the prior bias the results? The answer is yes, right? It is a part of what we are trying to use to estimate theta, right? And that's a good thing, right? If the prior is saying that theta can't be negative, we want that to be enforced in our estimate for theta, right? It is maybe worth saying that typically, except in very weird circumstances, you will have a large data limit property where if you measure enough measurements, the prior won't matter very much, right? Because the data will the likelihood will overwhelm the prior and you'll sort of converge to the value that matches the data well. When I say weird, in rare cases, if you say the parameter can't be negative and the data indicates the parameter is actually negative, so if your prior is ruling out the right answer, yes, you will get you will not overwhelm the prior because the prior has said there is zero probability of that, right? But that's what I mean by rare cases. Like, yes, if you encode wrong information, you will get the wrong answer. So I think it's worth saying that if you're doing this in practice, you probably want to document your assumptions pretty clearly. And it can be worth doing a sensitivity analysis to make sure that you're, that you're not biasing things in ways that you didn't intend when you wrote down what your prior was. Okay. And maybe if for frequentists in the room, it's maybe worth pointing out that you can think of the frequentist approach as Bayes with a very diffuse, or if you can manage it, uniform prior, right? So if the prior is telling you basically nothing, Bayes kind of reduces to a frequentist approach. The question is just really for a lot of cases, is it really appropriate to pick a uniform prior, right? It may not be, or it may be infeasible because maybe you can't pick a uniform prior on the space from -infinity to infinity, right? Or 0 to infinity. So you kind of need to then in the end say something about what the range of those parameters is at least. Okay, that's a bit of a spiel about priors. Okay, so really the idea here is that we're trying to model how humans understand things, okay? I think of us as Bayesian inference machines in a lot of ways, right? Like I walk into a room with some understanding of the situation, and then I observe things, and then I build a new understanding of the situation, right? Like, and maybe what I observe doesn't affect me very much if I already felt like I understood things very well, right? Maybe I view what I saw as an outlier or something, right? So yeah, so we start with our understanding of the world, which is the prior, right? And then we have an experience, and then we update our understanding, right? And yeah, this is what I was trying to say, right? If my understanding going in is vague, if I don't understand something very well, maybe that thing that I'm observing updates my opinion about things a lot. But if I already understand something very well, maybe data doesn't have too much of effect, like I need more data or very, very strong data to tell me what's different, right? So this is kind of what we're trying to sort of model how we build understanding of things as data accumulates, okay? Okay, so we're not going to talk really I'm not going to talk beyond this slide. I'm going to mostly be focused on Bayesian inference, which is how we estimate the parameter theta from the data y. But I did want to sort of say that there are other ways of applying Bayes. So this is one slide on Bayesian design of experiments, okay? So you can try to use Bayesian estimates of a parameter to design your next test. There were a few talks about this yesterday. And so the idea is that if you already understand the behavior of a system in certain parameter regimes, it may not be worth testing there as much, right? But if the behavior of a system is not as well understood in other regimes, you may want to focus your testing there, right? So that's sort of where the understanding from the prior, may be, may be useful in designing your tests. Just as I said, that frequentist methods are similar to Bayesian methods with diffuse priors. Bayesian DOE is similar to conventional DOE if you don't know very much or if you haven't taken very many measurements, right? Because in the end, it's sort of defaulting to the same kind of criteria for designing tests. Okay. One common concern with Bayesian design of experiments is that it's really hard to compute this integral that you need to sort of design to choose what the optimal experimental design is. I've seen a paper where of a R package that implements Bayesian design of experiments, and they say that it's typically only usable when the design space times the number of parameters is like less than or equal to 4, right? So not a very complex design space. And maybe this package was claiming to get it up to 8 or something, right? But it's hard to compute this thing. Or you sort of default to approximations of approximations of approximations, right? Which is another sort of, surrogate models and things like that. Okay. All right, so that's the Bayesian basics. Let me pause for a moment to see if there are questions. And also to say, you should feel free to interrupt me. We have a bit of time. So if you want clarification on something, please feel free to interrupt. Yeah.
Could you talk a little bit more about this comparison to conventional DOE, especially with regard to the priors and limited data, because all of our data out there in an operational experiment is going to be limited. So one of the things I was hoping to talk about is the prospect of updating the prior as you go, so that you can determine when you've got enough to go ahead and terminate the run, so that you may have already budgeted for and move on to something that's more insightful.
Yeah, and one thing that I have not talked about yet that I will talk about later is you can iterate Bayesian inference, right? If I collect 4 data points, right, I can, under most likelihood models, do my inference on the first point, use the result as my prior, do inference on the second point, right? And just sort of iterate that inference to build up an understanding. You get the same answer as if you do just inference with all 4 points, right? So you can build your understanding as testing is going on, rather than waiting until testing is complete to get the understanding. And so that's where, yeah, so even if let's say you start with a case where you don't have any data yet and your prior is weak, right? Once you take a few data points and you estimate your posterior, that can become your new prior, and then maybe you know things that will guide the next test, right? Because you've sort of started to nail down the behavior. You started to nail down your understanding of the parameter in certain regimes. Does that help at all? So then sort of once the uncertainty has been reduced in certain regions of the parameter space, maybe there's less incentive to test there because the posterior is already telling you, like, we understand this. Does that seem okay? Other questions? To how many people was what I've talked about so far new? Just a bit, okay. All right, so.
I have a question back.
Sure.
In general, theta could be a vector of parameters, not just a single
Absolutely.
scalar. Does it matter in your mind, for Bayesian DOE, if it's not a vector, it's a scalar? I mean, is it still the same computationally intensive? What's your thoughts on?
It's less computationally intensive because. Oh yeah, sorry. The question was, is this less computationally intensive if theta is is a single dimension rather than multi-dimensional? And the answer is, this is an integral over theta, so it's a smaller, easier to compute integral if it's if the parameter space is small. So yes, and that's a bit of what they were trying to get at here, right? Maybe you can do more with your design space if you have a smaller parameter space, basically. Yeah, and I don't want to discourage anybody too much. I mean, I saw a presentation at DataWorks last year where somebody, I think they were from Sandia, but I could be wrong about that. They were applying Bayesian design of experiments to a pretty complicated physical model, like in practice. Now, to approximate these integrals, they had to introduce a series of surrogates for the multi-physics model, so they weren't having to do a high performance computation on a cluster at every iteration of computing this integral, and then like a few other things, right? But they were able to sort of draw some inferences. It's just if you want to go down this route, just be aware of this limitation a little bit, and that you may need to do some approximations, basically.
You'd also, just to comment, but you'd have to have like really good reason to discard like a balanced design, I think, because a lot of conventional DOE is, like the full factorial is like the optimal thing if you can do it. And this, you're kind of opening yourself up to like not doing that.
Yep.
And so that's like, not something I would choose to do, I guess, under a lot of problems.
Yeah, because you're worried that there will be a region of parameter space that you think you understand, but you don't, right? Yeah, I understand that. Other questions? Okay, I'll keep moving. So okay, so I just talked about computational complexity of Bayesian design of experiments, but it's maybe also worth talking a bit about the computation of this posterior. Okay. Okay, so it seems a little bit funny, right? We have an equation for what the posterior looks like. So it's sort of like, well, can't we just write down what the answer is? And you can't. You can write an equation for it, but to get something meaningful out of that is actually non-trivial. And in particular, if you want to estimate things from the posterior, right? If you want to compute its mean, or if you want to compute its moments or its quantiles, things like that, you need a way to kind of draw samples from it, right? And for the most part, that posterior is not going to be something that it's easy to draw random samples from, right? We're not going to have like a function that we can call to say, draw a sample from this posterior. The exception is conjugate priors, which is where the prior and the likelihood are designed in such a way that the thing that comes out, is the posterior distribution comes from the same family of distributions as the prior did. Okay, and so just as a simple example, if we want to estimate the probability of success of a Bernoulli trial, often people take the prior to be a beta distribution for some choice of parameters, and then the likelihood is the binomial distribution, and then when you compute it, if you get S successes and F failures, you get out a beta distribution that's just your new alpha is alpha plus S and your new beta is beta plus F. So it just kind of looks like this. So I haven't shown you a prior or posterior yet, right? But if this is our prior here in green, and our true probability of success is this dashed blue line, right? As we take data, we're still getting a beta distribution. It's just moving to converge toward the truth as in this case, we have a bad prior, right? But the data is sort of starting to move the prior toward the true value as we take more coin flips effectively. Okay? But we will not typically be in this scenario. So often what we need is a numerical method to compute the posterior, to draw samples from the posterior. And a common tool for that is Markov chain Monte Carlo. And the idea is that we can't draw random samples from the posterior. So what we're going to do is draw random samples from things we know how to draw from, often a normal distribution, and then use those random samples through various methods to sort of turn them into samples from the posterior. Okay, and then we'll use those samples. We have a collection of samples from the posterior that we can use to estimate whatever we want, right? Whatever quantities of interest. Okay, and one key thing is that this doesn't require knowing the normalization constant, right? Because it's just a constant. It doesn't depend on beta. Okay.
Question.
All right. Yeah.
Can it accommodate non-random samples? In other words, theoretically guided or purposely selected?
So just for Zoom, the question was, can this handle like theoretically guided samples? And I guess I'm not totally sure what you mean. Like, I'm going to talk you through a simple MCMC, but ultimately, like the way I picture this is we have a probability distribution, and I can picture what that might look like in 2 dimensions. It looks like a hill or like a series of hills or something like that, right? And what we're going to design is methods that will traverse those hills or traverse that 2-dimensional space, let's say, and accumulate in ways that represent the hills. So there are a variety of ways they can do that. They can take into account the simple ways are just drawing random samples and just randomly traversing that space. The more complicated ways are including things like the gradient. So like which way is uphill and which way is downhill where I'm sitting, right? And so they will use various dynamical ways to sort of like incentivize going uphill and disincentivize going downhill and that type of thing. I don't know if that could be a wildly different answer than what you were asking. I'm not totally sure.
Definitely touches on it. So thank you.
Okay, all right. And just to be clear, I'm talking about a hill in 2 dimensions because I can't picture a hill in 3 dimensions, but or 10 dimensions or 100 dimensions, right? But in principle, the same ideas should translate. So just to give you a flavor for what these MCMC methods look like, I'll talk you through the original example that goes back to, I believe, Los Alamos in the 50s. So this is random walk Markov chain Monte Carlo. So really the idea is we're going to draw we're going to start with a sample. We're going to draw a normal distribution around that. So we're going to draw some proposal, okay? and then we evaluate where we are and the proposal. And then we either, the rule is you always go uphill. So if the probability of the proposal is higher, you always go there. And if the probability, so if I just leave it there, it's like a maximization routine, right? It's always going uphill, never going downhill, right? But with MCMC, we also want to explore the tails of the distribution. So we sometimes let it go downhill. And if you pick those probabilities just right, here, this acceptance probability just right, in the end, you get samples that look like the target distribution, okay? So this is, this is the simple, this is sort of the simplest of these algorithms in a way. There are a variety of other samplers. I found this link, which may be hard to write down quickly, but this is sort of a GUI that you can click on a method and tweak parameters and tweak the target distribution and watch it visualize how it's traversing the posterior. Okay, so these can be quite complicated to implement, but the nice thing is that there are a bunch of implementations that somebody else wrote and maintained, so you don't need to. And lots of them have like wrappers in R, for example. Like RJAGS is a very popular one, and Stan is a very popular one. So yeah, so don't feel like this is too intimidating because people have already done the hard work for this. Just another making you aware thing. We talk in well, not me so much, but people talk about confidence intervals in frequentist statistics. There's an equivalent in Bayesian statistics which are just called credible intervals, okay? So just simply, an example statement in frequentist statistics, I really hope I'm not gonna get this wrong. If we ran an experiment 95% of the time, if this is our confidence interval, we would expect the parameter to live in that confidence interval that we compute in each of those experiments. In Bayesian statistics, right, we compute the posterior, and then if we measure that posterior on an interval, right, this I'm assuming a one-dimensional parameter, then we're saying that the, if that posterior measure of that interval is 95%, then we would say, with 95% probability, the parameter lives in that thing, right? So we're drawing our hills, and then we're just computing the area under that hill effectively, or the percentage of MCMC samples that live in that set, and we're saying that's the probability, right? So that's how we would do it with MCMC. Okay, any questions about that before I talk about integrated T&E? Okay. All right. So I hinted at this after the question earlier. This is sort of how I picture Bayes applied to integrated T&E, right? So as a system is developed, there are a lot of there's a lot of data that is sort of collected. So here I've just because they have lots of fun public images, I've taken pictures from the NASA's quiet supersonic program that I learned about at DataWorks last year, actually, during a very nice plenary. So they have nice pictures of simulations and tests and things like that. So I use that. So there are a lot of different data sources, right? So we have maybe historical systems. I don't know that the Concorde is a great proxy for NASA's quiet supersonics, but there are in principle things we know before we start testing the system, right? They're doing simulations, right? Not that this is necessarily DT, but it was a neat picture, right? They're doing testing as the things developed. In principle, they could move on to OT, right? So as we're developing systems, data is accumulating, right? And the vision is that we would like to build an integrated understanding of the system as it's progressing through this, okay? Using all of this data. Okay, so I sort of said this earlier. So a nice thing is that, you know, I can iterate Bayesian inference as data is coming in, right? So yeah, I really want to show a picture, so I'm going to come back to this and well, okay, maybe I'll just say one concern here is that, well, this only holds, like, I can only get the same answer by iterating inference over the data if my data is sort of drawn from the same process, right? If something hasn't changed, if the system hasn't changed, if the environment hasn't changed, that kind of thing, okay? So an issue we would have, right, is that this system is not necessarily the same as this system, which is not necessarily the same as this system, or we're adding factors in what we're testing, right? Like either the system or the environment is evolving as it's developed, right, and as it's fielded. So we don't want to treat data from this or data from this as equivalent to data from over in this range, right? We want to maybe trust this data more. Okay, so there are, you know, people are thinking about how to do that translation, right? A really simple idea is downweighting. So we could, for example, if we get a posterior that looks like this, we could say, okay, I believe this posterior from DT, right? Like we've tested it a lot. I believe this estimate, right? But now we're going to go to OT, right? And the environment's going to be a little bit different. Maybe I don't believe, like maybe I trust the point estimate, the mean or the peak, pretty well, right? But maybe I don't trust it as much as I did if I was just doing more DT, right? So what I'm going to do is leave the mean the same, but just add uncertainty, right? So there are thoughts about how you can sort of, you know, so what that effectively is saying is that we trust DT, but we don't trust it as much as if we were doing more DT as we're going into OT, okay? So the idea, roughly, is, right, like this is a single test phase, right? So we're gonna start with our prior, we're gonna collect some data, we run it through this Bayesian machine, right? And we compute our posterior, we have our new estimate. But then what we would like to do is we're going to take that new estimate. Now we're ready to collect new data, right? So we adjust it as we need to based on the context. And that becomes our new prior, right? And then we run our next test phase. And so then what we end up in the end is just this iterative procedure, right? Where we, you know, at the beginning, we start with a prior, collect data, compute our estimate of the parameters, adjust as necessary, move on to the next test phase, right? And throughout, we have this estimate of our parameters as the system is evolving. Okay, so that's sort of the dream about how you could apply Bayes to this sort of continuous testing, let's say, that the director of DOT&E talked about yesterday. Okay, so that's where we are. Are there questions before we move on to Adam's piece with the example? Okay.
Yep.
I need to do something to mute this.
Yes, but I don't know what it is.
Okay.
I'll just give you a short intro, Adam.
Oh, sure. Yeah.
So moving on to the next phase of our tutorial, I'm very pleased to introduce Adam Ahmed. He is a research scientist at Metron and is the technical lead for Metron's DOT&E effort. His research interests include applying novel Bayesian approaches to testing and evaluation, machine learning methods for small data sets as applied to undersea mine classification, and time series classification for continuous active sonar systems. Dr. Ahmed holds a PhD in and a master's degree in physics from the Ohio State University. So,
There we go.
you're supposed to say it that way, I was told. So, this one's you, right?
Yes.
Okay, good deal.
All right, so here is the setup that we're going to be talking about for the rest of this part of the tutorial. So you're part of the T&E Working Integrated Product team to test something called the Mach cannon. Okay, so it's based off of the 155mm howitzer. You're working alongside Bayesian-trained SMEs brought on by the product manager on inference for operational testing and evaluation. So you and those Bayesian SMEs have already assisted in formulating the detailed test plan, but now there are requirements laid out in the testing and evaluation master plan. And given those requirements, you have to evaluate the viability of the Mach cannon as a potential capability. So let's talk about the system under test, the Mach cannon. Okay, so it's based off of this 155mm howitzer. And the temp defines an accuracy metric, which basically you're going to have to look at to determine is the Mach cannon a viable product or not. And so what you'll do is you'll fix the cannon in some kind of configuration, you'll shoot it a bunch of times, and now if we look at the scatter plot, the requirement is based off of a circular error probable. So basically you take a circle, lay it down on top of this scatter plot at its center, and ask, what's the proportion of those fired shots that land within the circle? For us, it'll be a CEP-Z criterion, so it'll be a CEP50 criterion, saying if you get at least 50% of the shots to land in that circle, it's an acceptable system. Otherwise, it's not an acceptable system. And that radius that we're going to be measuring against, for us, will be 100 meters. That is that CEP radius. Okay. So this portion of the tutorial, I've broken it up into two parts. One is applying Bayesian methods and Bayesian updating to this Mach cannon system. And so we're going to address the question, given that you've conducted a test and an experiment, how do I apply Bayes' theorem? How do I go from a prior to a posterior? And so we'll go through these steps of defining a model, a likelihood, a prior, the associated hyperparameters, and the posterior. And then the second part will address the question using something called Bayesian decision theory, which is, should I even conduct that test? Is it worth it? And how do I evaluate the worth of conducting that test? And so we'll define some new terminology to address that question, where we'll define states, actions, outcomes, how to measure your preferences, and then how we project out future states to address that question of, should I conduct a test? Okay, so for part one, applying the Bayesian methods and Bayesian updating to the Mach cannon. So to get some more details of what this thing is, the munition itself is based off of the M107 high explosive artillery projectile, and it'll only be shooting unguided munitions. Okay. And the independent variables we'll be concerned with are range, which will be the distance from the Mach cannon to the point of impact, and the quadrant elevation, which is the angle that the barrel makes with respect to the IJ plane, the horizontal plane. The dependent variable that we're going to be interested in is the point of impact error, because that's the quantity that's directly comparable to the CEP radius. And so we can see if it's, less than that radius or greater than. So in this universe, maybe there is a console, on the Mach cannon. You type in, okay, I've set it to this angle and that. Maybe put in a munition. You get some predicted impact point. You'll fire that munition, and then there will be some distance away. That relative distance is what is called the point of impact error. Okay. Now, there are several contributions that go into this Mach, how the projectile flies through the air, and there are some forces, some main forces that are associated with it. We have the gravitational force, we have the drag force, the munition is flying through a fluid, we have the lift force. And turning on those forces one by one, we can see the trajectory just with the gravitational is a nice parabolic path. With the drag force, it's resistive, and so the range is significantly shortened. And with the lift force, we can get a lateral drift. In addition, there are some rotational kinematics as well, and there's some environmental conditions. But from the perspective of the tester, all these details are just kind of abstracted away. And from the tester's point of view, they'll fire ammunition and they'll measure range and quadrant elevation. So they'll collect data in maybe some kind of tabular form like this, angles and ranges. On the other hand, they'll measure the outcome. In this case, they'll calculate the point of impact error, and they'll collect the associated point of impact error per experiment they conduct. But to really assess the Mach cannon and to say, is it good over all operational environments or contexts that I'm interested in, we would like to know the mapping between an experiment to its outcome. And so that mapping we can define with a model. And so in this, how we're going to define a model here, it's a specification between the parameters, theta, and the observed data. So our outcome or response variable, point of impact error, can be written like this. Y is equal to some function that takes in the context and the parameters, plus some noise term. So that first term is called the deterministic component, defines the exact relationship between those parameters and the context. And then there's a stochastic component, because if you repeat that measurement at the same x, you're not going to get the same. There's some underlying error that we can't account for in our model. So what we're going to assume for the Mach cannon is that our model is linear, and we'll define it as, for the deterministic component, this matrix product of the contexts times the parameters. Expanding that out, we'll see that what we're going to do for the Mach cannon is we'll say we'll have an intercept term. We'll have a term that depends on the range. We'll take log of the range here, quadrant elevation and radians, and then if there's any kind of curvature kind of response that is in that deterministic component, we'll account for it for a cross term. Next, we need to assume some form of the stochastic component, the noise in your data. And so we'll assume that it's normally distributed with the zero mean and a variance sigma squared times I, where this I is the identity matrix. Okay, so now that the model is fully specified, we can define the likelihood of getting a particular outcome given a particular parameter, theta, or coefficients theta, and context x. And so that will be a normal distribution for us, where the mean is simply that deterministic component, and the variance is that variance from the stochastic component. And one note is that because this is the likelihood of outcomes and it's normally distributed, we want to make sure that our outcome kind of obeys or is in agreement with our assumptions. So when we took a look at the data, we found that taking log of point of impact error was more normally distributed. So for the rest of this talk, the outcome variable will be log point of impact error. Okay. Next, as part of this trying to apply Bayes' theorem, right? We've defined the likelihood. Now let's define the prior distribution. So the prior is the probability distribution over the parameters. And for the Mach cannon, we'll make an assumption that theta is a random variable. Right? There's a probability distribution associated with it. But this thing sigma, that's that variance from the stochastic component, is known. So I'm just going to set it to 1 and just say that's 1 for log point of impact error. And so one way we can think of theta as being a random variable is in this cartoon down here, if I'm plotting y versus x, the thetas, which are in this linear model slopes, we can think of it as now we have a distribution of slopes that are trying to represent these blue data points, right? So with these assumptions, and what we'd like to do is use Bayesian conjugate prior structure, because we don't have to take these very difficult integrals. We can actually calculate the prior to the posterior very simply. So we'll have a normal distribution for the likelihood, a normal distribution for the prior, and what will happen is we'll get a nice normal distribution for the posterior. Okay, so the prior is a normal distribution, and it'll be a multivariate normal because we had 4 parameters: the intercept, the range, quadrant elevation, and that cross term, so it's 4-dimensional. But it's a normal distribution with a mean of mu, and then a covariance matrix of sigma squared times v. And so now I've introduced 2 new variables here, mu and v. So what we like to say is that there are parameters that characterize the parameter distribution, and so we call them hyperparameters. They define our knowledge about the state of the Mach Cannon system. And so we'll collect those hyperparameters in a thing called kappa. And one example is, if I give you the mean and the variance of a Gaussian, you know the entire distribution after that, which is why we say this is the hyperparameters define our knowledge. Okay, so we have the likelihood, we have the prior. Now we want to update to get the posterior distribution. And so because of this conjugate prior structure, if the prior was normal, that means the posterior is a normal distribution, but it'll have slightly different hyperparameters. And so going from the prior to the posterior, we'll denote it with a plus, a mu plus and a v plus. So the way you go from the prior is you need to have some kind of data, some kind of update to your knowledge. So let's say you conduct n trials in environments X, okay, some matrix X, and you measure those associated outcomes Y. Then a knowledge update, which takes you from one hyperparameter vector kappa to the new hyperparameter vector kappa plus, is given by these set of equations over here. Okay, looks a little ugly, but if we do a change of variables, letting w equal the inverse of v and nu equal to mu times w, then it looks a lot more simply written over here, where the old hyperparameter for w, or the new one, is equal to the old one plus x transpose x, the covariance in the data you collected. And the new is equal to the old nu plus y transpose x. And so this is just to illustrate that using this, when we're looking at this conjugate prior structure, that like the data literally adds to your knowledge. Right? So that was a lot of equations, but let's take a look at an example with some numbers. So let the prior hyperparameter vector, the knowledge, kappa, be this mu equal to 7, 1, minus 1, 1. Okay. And the variance associated with the variance of the parameter distribution be this diagonal matrix of 1s times 10. And so what we're going to do is say, let's say you've collected this data over here. You've collected 3 data points, 3 experiments, and the associated point of impact errors, or log point of impact errors. How do I perform this update? Well, we'll convert our mu and v to w and nu. Okay, so we'll get this inverse of v, so that's 10, 1 divided by 10 is 1/10, which you can do for diagonal matrices like that. And nu turns out to also be 1/10 of the original mu. Then you can just apply these equations where the w is x transpose x, so we're taking this x matrix, taking its transpose, multiplying it by x, getting something that looks like this, and updating nu to nu plus is something that looks like this as well, taking y transpose, the y over here, times x transpose. At the end of the day, we want to compare our new v and mu to the old mu and v, because we want to compare this prior hyperparameter vector to the posterior hyperparameter vector. And so we can see some outcomes from this, that if we look at mu plus, we can see that the mean has changed a little. We went from 7 to 6.33, 1 to 0.31, yada, yada. But if we look at the variance matrix and just focusing on the diagonal components, before v was all 10s, and now it's saying for the first 2 components, which relate to the parameter for intercept and quadrant elevation, The variance went from 10 to 8.2 to 8.8. The variance decreased a little bit. However, if you look at the other two, which relate to log of range and quadrant elevation, in the cross term, the variance decreased by 2 orders of magnitude. And so it's telling us something. It's telling us that it learned something important from the data and therefore became much more certain about those parameters. So, okay, that's just looking at, a matrix of numbers, but now let's take this matrix of numbers and look at the associated prior and posterior distributions. So I'm going to look at the marginal distributions. So that means I have some 4-dimensional normal distribution, but I only want to look at each parameter individually. So I'm going to integrate out all the other parameters and just leave the one I'm interested behind. So I'll take this 4-dimensional thing and I'll just get a nice 2D plot. And so for the intercept and the quadrant elevation, going from blue, the prior, to the posterior red, we can see, okay, the mean shifted a little bit, the variance didn't shift much, and that was that 10 going to 8.2 that we saw in the matrix. But here, it learned quite a bit from those 3 data points. That's saying, oh, that I know how range is going to be predicting point of impact error, and so it became much more certain about where that value was supposed to be, and then the spread in those parameters. Okay, so that concludes the first part of how to perform this Bayesian updating for the Mach cannon, right? And this process repeats iteratively. So if you did get another set of data, your posterior distribution and your posterior hyperparameter vector become the prior for that for the next step. So before I move on to the next part, I'm going to take 2 asides, just 2 comments about what we just saw. 1, setting the prior. Well, in that example, I asserted that kappa was this mu of 7, 1, minus 1, and 1, and v was 10. Well, okay, but where did that come from? Well, you have to set it. So setting the prior usually takes some SME knowledge about the system. And when little is known, typically you set the mean to 0 because you're like, I don't know what the values are supposed to be. And then you set the variance matrix to some large number where you're like, the parameters could be, I don't know, minus 1,000,000 to 1,000,000. Okay. But we can do one better, especially with related to like physical constraints. So one thing is that the intercept is a really nice coefficient term because it shares the same units as point of impact error. So we can start thinking in terms of possibly the requirement units. And so what we're going to do is we're going to be conservative. The requirement, that CEP radius, was 100 meters. So we'll be conservative and we'll say, okay, the Mach cannon, its point of impact error is something larger. We're going to set it in a region where it's not going to pass. So we'll just set it to like 500 meters, which then means after you take log of 500, you get 6.2. Variance is a little more tricky because there's many more things to set. So what we'll do is we'll just have v equal some coefficient times a diagonal identity matrix. And we'll observe the effect. Specifically, we'll observe the effect on something called the prior predictive distribution. And so this distribution is the probability of y integrated over all the parameters that this system could be in, that prior distribution. And after doing that, normal distributions are very nice. You get another normal distribution, but now with a different mean and a different variance. And so we're going to observe the effect of the probability density function as a function of point of impact error. One comment I'll make is that because we're looking at log point of impact error, I want to look in physical units again of just point of impact error, which is in meters. So these are log normal distributions. There's a transformation that you can do. Up here it says posterior predictive. It should say prior predictive, but okay. So let's take a look. What if I set lambda to something like a small value, so a small variance? Well, what'll happen is that these will turn out to be pretty narrow priors. How do I know that? Well, if I look at the probability distribution and I look down here, it's saying the Mach cannon's point of impact error has 0 probability that it's less than 150 meters. It's like I'm saying that this thing will never pass the requirements. Well, I don't know that. So this turns out to be a narrow prior. All right, let's look at the other end. So you have, let's set it to 10 to the 0. So I'm changing this in orders of magnitude of 10. This turns out to be an unrealistic prior because you have a mean of 8,000 meters and a variance of 82 miles. So I'm going to go ahead and say that's not realistic, and I'm going to ditch this assumption. So if we set it to 10 to the minus 1, we kind of get best of the both worlds. Mean is around 700-ish, variance is around 800-ish, and so it's saying like the point of impact error can be between 0 and 1,500, 2,000 meters, a mile. And you're like, okay, I don't think it'll be off by a mile, but at least it's in the realm of reality. And that's how you want to set the priors. This is an example. There are many different ways that you can set priors, but this is just a way to do it. Secondly, well, the Mach cannon is not real. Surprise. Okay, so we have basically simulated this Mach cannon basically with a 6 degree of freedom model. But the point here is to just show that if you do the full modeling, this is the full response surface if we're plotting quadrant elevation by range by point of impact error. It's some highly non-linear surface. This is the universe. This is what's really happening. And our job is to represent that unknown universe. And so that's pretty difficult, but I just wanted to just take that aside to just show you what that response surface was. Okay, that's the first part. And now we're going to talk about Bayesian decision theory, which addresses the question of, should I even conduct a test? So, does anybody have any questions before I go on to the next part? Yes. Yes.
You write down the prior predictive
Yeah.
distribution on the bottom. Could you clarify what you are showing on the right-hand side?
Yeah.
It's not the prior predictive, it's the posterior predictive.
Yeah, so it should say prior predictive.
Okay.
I forgot to. Oh, okay.
Posterior predictive with no data.
Yes.
So Adam,
Yes.
let's say you and I are both in the same IPT, and your prior predictive is that the CEP is 700. My prior predictive is that Mach cannon is awesome.
Yeah.
It's gonna destroy all of our enemies. CEP 20.
Sure.
Okay. What do we do?
Well, for that case, that's totally fine that our priors are different. It's just how much weight you want to associate with that prior, right? So when I'm setting a prior here, even though it has this kind of a distribution, I'm not going to associate a lot of weight with it, especially because I don't know much about the system. You, on the other hand, could have tested several different howitzers or different, cannons in your life, and so you have a lot more knowledge about that. And so you can set a prior and say this is a lot more specific, and so that's totally fine.
No,
But if you had a
it's just that my promotion hinges on the system passing the requirement.
oh, conflict of interest, I see. Well, okay. Well, then, yeah, you can do that, I guess. But did you have a more specific question than that, or?
Well, I mean, you're going to do your analysis based on your prior.
Yeah.
I'll do my analysis based on my prior.
Right.
We could come to different conclusions.
We could come to different conclusions, right? And then, of course, that's a function of the data, right? So as you collect more and more data, then the priors become less important, and will both converge to the same answer. It's just in the limit of when you're only looking at a few data points, then that's where the discrepancy will be. Did that?
Your distribution is narrow also. It's not just that
Yeah.
it's not just that the mean is small, it's also that you're ruling out kind of the higher values. Okay.
So, I mean, we say that somewhat jokingly, but if a member of the test team said, oh, these shots shouldn't count because of whatever reason, and you remove a couple outliers, that's going to dramatically change the answer that you're able to achieve with relatively small amounts of data, right? Relatively small number of live air testing.
Do not decide it's an outlier until you make it.
So the assumptions and the weighting factor that you choose to apply to this can really skew, so it opens the door for people achieving the answer they want to achieve with the same set of data.
But the other thing is you've computed the prior predictive. So if you get results that don't back up the notion that this is a wildly awesome cannon, then you can just simply say, okay, the model would lead us to say that the data leads us to reject the model.
Sure. Right. So there is some care that needs to be done. Seriously, there really does need to be care. You need to work with an SME, and really, if you're setting a prior, other people should be looking at it, and sort of you want to kind of get a wider breadth of kind of SME knowledge versus putting in just your own biases and beliefs in that prior.
Well, so something you pointed out here, Adam, that's good. It's like the blue and the orange one. The fact that they get so small in where the correct parameter actually lies, that's a way. There needs to be careful elicitation. So if John wants to put his thumb on a scale like 20 meters, you've got to look at the implications of that for a range of things. So if he ends up, so you're then making an assertion. It could be like the probability that it is 100 meters is like 10 to the negative 40th. And now maybe you don't want to put your thumb on that hard, because if you're held to task for that assertion, it's like really less likely than winning the lottery like every day of this week, right? So, as long as so the Bayesian techniques make all your assumptions, they bring them all out into the light. And so once everything's in the light, there's less motivation to you're leaving your fingerprints when you put your thumb on the scale.
Comment I'd like to make is some of this conversation here about putting your thumb on the scale, or can you decide that certain examples are outliers and then remove them? The other part to the conversation in testing is the data itself. And so if there are outcomes here that you aren't comfortable with, perhaps the data can enter into the conversation. Like, for example, the data will eventually swamp the prior. So maybe that puts a requirement on the data. If you're uncomfortable with how much influence the prior has on your conclusion, then that puts a requirement on how much data you. If you're uncomfortable with the way that an outlier in the data can change your answer, then you need a concept of vetting or validating the data so that one single person can come in and change things. So I just wanted to point out that there's another part to this conversation, which is the data.
So Austin, like to that point, something I like to do when I model, like when necessary, is kind of add on one level of hierarchy where it says there is some probability that I'm going to have an outlier, right? Then it'll either be some crazy outlier or it'll be something that fits my base model, right? And that way you can automatically, you can't throw in like 10 to the negative 100th, some sort of, or nan or something. It'll just say, okay, well, obviously that's an outlier. It'll put it over there, and it won't, like with these linear models, they're very rigid. You wouldn't want to throw a 10 to 100 into one of those, because that would be the entire story.
Okay, so
One small comment.
yeah.
So you had normal plus like times of normal gives you a normal.
Yeah.
One thing just to keep in mind is that that's because of the linear model, right? If the model was nonlinear, then you would have a nonlinearity baked into the normal instead of the posterior.
Yeah.
Okay. I just wanted to clarify that because I harped on the conjugate prior versus similar. Right. That's all.
Okay, so for the second part, we're going to discuss the question, Should you conduct a test? Is it worth conducting a test? And so we're going to use a branch of decision theory called Bayesian decision theory. But we're going to need to just understand decision theory at first. And so I'm going to set up some terminology and kind of get an idea, kind of get ourselves oriented to like, what is this thing? Okay, so some decision theory, just basics. Okay, so it's a branch, decision theory is a branch of probability that relates your beliefs and your preferences between making choices between alternatives. And we'll concern ourselves here with making normative, using normative decision theory. So that means we're going to identify optimal decisions, assuming that the person making those decisions is a fully rational person. And I'll explain what rational means later on. So, given two outcomes of the universe, A and B, we can express our preferences with these sort of like curly greater than equals signs. Okay, they're preferential operators. So this is A is strictly preferable to B if I always prefer A over B. I'm indifferent between them, and if that's the case, I'll give this like tilde. And then I'll get this curly greater than or equal to sign where I'm saying A is weakly preferable to B if we sometimes prefer A over B or we're indifferent. Okay, these are qualitative descriptions of preferences over these two outcomes, but we can take these qualitative descriptions and then put them through a real valued function, we call it the utility function, that maintains the ordinal relationship between our preferences. So then we say U of A is greater than, now we use the regular greater than sign, greater than U and B, if and only if A is strictly preferred to B, and same thing with the equals if we're indifferent. Okay, that's the first part. So now we need to define this sort of decision space, some more terminology to sort of get us oriented here. So there will be three things we'll be concerned with. One is the state space. These are realizations or configurations of the universe. Two is the action space. And so these are actions that we can take such that we start in a state and it'll get us to an outcome. And the outcome space is that consequence or the reward of that joint state action. Okay, and there will be an example right on the next slide because this is just a lot of words here. We will then take, after setting up the state action outcome space, we'll then define our preferences. And then those preferences for each of those outcomes will be mapped to the real numbers, some numbers called using the utility functions. One thing I want to note is that a utility function is elicited, and it encodes the agent or the person making the decision, encodes their preferences. My utility function can be different from your utility function. So here's the example. Should you take an umbrella? Okay. The state space is the weather forecast. So we'll consider two states of the universe, that it's either sunny or it's raining outside. The action space is either you take an umbrella or you don't. And the outcome space is the consequence of having or not having an umbrella in different weather conditions. And so that's that joint action space that I was talking about. We're talking about the outcomes. So here we have the state and the action. It's sunny and you don't have an umbrella. The outcome is you're dry. Great. Now you're sunny, it's sunny, and you have an umbrella. Now you're still dry, but you're encumbered, meaning you now have to lug around an umbrella the whole day. Similarly, if it's raining, we'll define the outcome as raining and no umbrella, you're wet. And then raining and umbrella, you'll be dry, but you'll be encumbered. You'll still have to carry an umbrella around. Okay. Now that I've defined the state action outcome space for this example, we need to define our preferences for those outcomes and then the utility of that preference. So for me, I'm going to say being dry is strictly more preferable than being dry and encumbered and carrying an umbrella around, which is then strictly more preferable to being wet. From there, I'll take these qualitative representations and I'll make them numbers, okay, with the utility function. And for me, I'll say being dry, best case. I'm going to give it a 1. Being wet, terrible day. I'm going to give it a 0. But this dry and encumbered state, we'll give it some middling value. So for me, I'm going to give it a 0.8. Okay. One thing I want to point out is that you can think of some actions as having costs. And so the utility of this dry and encumbered state can be thought of the utility of being dry minus the cost of carrying an umbrella. Okay. And so that's 0.2 for me. And so I assign that a 0.8. Other people could rank their utility for carrying an umbrella. It could be a super painful experience, and it could be, I'm going to give it a 0.2. Okay. Okay. But what we're really interested in is making decisions under uncertainty. Where does the uncertainty come in? Well, the uncertainty comes in when you don't exactly know what the state of the universe will be. So in this example, that uncertainty would come from the weather forecast. And so we say that for this example, there's a 70% chance it'll be sunny, a 30% chance it'll be raining. We'll take all of those states and actions and outcomes, and we'll collect them into something called a decision table, where we'll put the states on the horizontal axis, the actions on the vertical axis, and we'll collect our preferences and the utilities here. Now, we ask the question, well, what is the best action I should take in this situation? We're going to use something called the principle of maximum expected utility, which says, well, if I have uncertainty about the state of the universe, the optimal action maximizes the expected utility. And I'm trying to maximize this expected or average utility, which encodes my preferences. So for the no umbrella case, what I'll do is I'll take this expectation, which is the utility times the probability plus the utility times the probability, all of this, and I'll add that up, and I'll get 0.7. On the other hand, I want to calculate the utility of taking an umbrella, and so that's 0.8 times its probability plus 0.8 times its probability, you get 0.8. The rational actor will always choose the situation that maximizes the expected utility. And so someone who is rational would choose the 0.8 and would take an umbrella in this situation. If you choose anything less than your preferences, we'll call that irrational. So you would not, or someone not taking an umbrella would be irrational in this case. Okay, but how do we apply this decision-making scenario to the tester's perspective? Well, the tester has to make a sequence of decisions, and so this is sequential decision theory, but they'll kind of go through this process. They'll have some knowledge state kappa, that hyperparameter for the prior distribution, and they'll ask themselves, do I know enough to accept or reject the Mach cannon? Is it good enough? Well, if they say yes, great. Tester's job is done. They don't have to do any more tests. They say yes, they send it off. They say no, they send it back to the developer. So we call that a terminal decision. It terminates the decision process for the tester. On the other hand, if you're like, well, I know this much about the Mach cannon, but I don't want to make a definitive like yes or no at this moment, we'll call that a non-terminal decision. Or an intermediate decision. So if they say no, they'll conduct a test and they'll update their knowledge after doing a test from this kappa to the kappa plus. They'll go from a prior to a posterior distribution and repeat this process until they are confident enough to get to that terminal decision. So we also say that the terminal decisions influence the non-terminal decisions influence future terminal decisions. Now, what we're going to do is define the state action outcome space for the Mach cannon. So our state space here are these uncertain parameters. We'll call them states here. So we'll define it as theta, or we'll say theta given kappa. Theta given that I know this much about the prior distribution. Bayes' rule, the Bayesian part takes care of that uncertain probabilistic distribution over the states. Before we had the weather forecast. Now we have the prior distribution giving us those probabilities for each state here. The action space we'll define as accept the system, reject, or continue testing. And we'll further kind of split this up as a terminal decision is accept or reject. And the outcome space no longer has to be some discrete outcome of like dry, wet, 1, 0.8. It can in general be some continuous valued thing here. Okay. So now that I've defined the state action outcome space, we now need to define the preferences of those outcomes and then the utilities associated with those outcomes. The reject utility, by far my favorite, it's the easiest one to think about. If you reject the Mach cannon, send it back to the manufacturer, it adds no value to you. The utility of a rejected system is 0. Okay. Next, the accept option. Okay, it's a little more complicated, but now we have to represent our preference depending on when we would accept the system. So our preference will be relative to the containment probability. What's that fraction of points that was contained within that CEP circle? The more points, the higher the fraction, the more accurate the system. So I'm going to say my preference corresponds to how much of that fraction is in that circle. And so what we're going to do is we're going to integrate the likelihood distribution for a given x and theta. And if I have more area integrated, that means it's a more accurate system. More points were within that circle. If I have less area, that means it's a less accurate system. And so this is a more preferable state, that's a less preferable state. Furthermore, my preference is with respect to the requirement threshold, where I'm going to say, okay, well, this requirement threshold of a just passing system was the CEP 50%. If 50% were passed. So I'm going to define a utility function relative to this 0.5 that says I'm going to give a utility of 0.5 for just passing. You just gave me a barely passing system. If you gave me a more accurate Mach cannon, my utility will go up. And quickly on the same end, if you give me a less accurate system, my utility will go down. Finally, the accept utility then says, give me the expected utility over all of those states, all of those thetas, minus the cost of choosing the accept option, the accept action. And so that here, and it's like one example of a cost is like, okay, if you accept the system, now you have to buy it, right? So there's a cost to doing that. And so this is the accept utility. The terminal utility then follows from this principle of maximum expected utility, which then says the terminal utility is the max between these two actions. Okay. Lastly, the last action in this case is the testing utility. So we need to define our preference and the utility. This is a little different because we're trying to address the question of some future outcome that we don't know about. So we can phrase a question of what is the value of conducting another set of tests, an environment, and some tests that I want to conduct x sub t, right? Another way of evaluating this continued testing action is, would a future test that I want to conduct yield a whole higher overall terminal utility? So because we haven't conducted the experiment, right, we have the points we want to measure at, and we're trying to determine is that a good set of tests. What we're going to do is we're going to project out future states based off of our knowledge today, based off of kappa. And so we will sample outcomes from the posterior predictive distribution in a similar way. And so there's this normal distribution. And so we'll say, okay, these are the tests, these 3 data points I'm considering, should I do this test? I'll say, well, one outcome of performing this test is I'll sample from the posterior predictive distribution, and I'll say, okay, maybe this is the outcome. Or I'll pull another point from this distribution, and I'll be like, well, maybe this was the point of impact errors for all of this test. And I'll sample several times and look at several realizations, several different like universes of conducting this test. Before we were looking at decisions for like that umbrella case where we said, okay, let's look at a decision table. For sequential decision theory, we're going to look at a decision tree. And so what we're going to do is we're going to visualize this for a one-step look ahead, just for the ease of drawing this out on a slide. So we're going to project out all these possible outcomes of performing a test. So say I start with some distribution and some knowledge kappa, some hyperparameter vector kappa. I'm going to say, well, if I conducted this test x and I had an outcome y, I'll get a new kappa. And that's from those update equations that I showed you earlier before. Then I said, well, what if the outcome was this for that test? Well, maybe it's kappa 2 plus, maybe it's kappa 3, maybe it's kappa 4, and you do this many, many times. Okay. This is our so-called forward propagation steps. We're going to push into the one step forward into the future. And then we'll say, okay, well, let's say I conducted a test and I said, now I make a terminal decision. I only do that one test. I will calculate the terminal decision utility for each of these kappas. And then I'll say the testing utility is the average of all these future utilities minus the cost of performing that test. And so that's how we define the continue testing utility, is the average over these future states minus the cost of that test. And then we'll take that utility and we'll back propagate it back to kappa. So now finally we arrive at the optimal action you should do. The optimal action over the 3 actions we've defined, you could have accepted the system, rejected the system, and you could have continued testing. Well, now that's that principle of maximum expected utility. Now we're just going to take the max over those 3 utilities. And again, this process repeats sequentially until the intermediate action, the non-terminal action, continue testing, is no longer optimal, and therefore you need to make a terminal decision. So in this example that I'm showing here, I said, oh, okay, well, my test matrix is 30 test points. I'm showing the first 3 rows here. There's 27 more. And I calculated these utilities for the accept, reject, and test options. 0.10 and 0.14. So 0.14 is the max, and that was corresponded to the test utility. So in this decision process, it recommended you should probably do that test. You'll probably get a higher overall utility. Looking at comparing the prior predictive before doing the test to the posterior predictive after doing the test, it recommended doing the test, and this is how the distribution sharpened up after performing that. And so it became much more certain about the distribution of point of impact errors for the Mach cannon. Okay. So in summary, we talked about a few things. We talked about setting up a model, a likelihood, evaluating that model by integrating that likelihood. We talked about how to do that knowledge update for the Mach cannon, going from a prior to a posterior, and one potential way you could be setting a prior. And then the second part was Bayesian decision theory. So how do we define the decision space? What are the states? What are the actions? What are the outcomes? After you do that, you say, well, I need to define the preferences of those outcomes, and then I'm going to take those preferences and make them a utility. We have a utility function that does that. The most optimal action after doing that is that rational agents maximize the expected utility. And so that's that principle here. And then lastly, how do we evaluate that continue testing option? Well, we do that by saying if I want to do a test, a future test, well, I need to simulate out what the future options will be, calculate a utility from that, and then that completes your sequential decision process. Questions? Yes?
So like in the 30 runs that you selected there,
Yeah.
how do you know what would lead to the maximum utility for test? There's lots of different options for quadrant elevation and whatever, those 2 factors you had there. So how do you know what factor level settings and whatever to run to maximize your test utility or something like that?
Right. So I'm not optimizing that. This sounds like more of a design question.
Right.
This is if I had a test and someone said, these are the 30 test points you need to perform. Now I need to decide, okay, is it worth performing this particular test? Or is it not worth it and I should just say, oh, the Mach cannons, I should accept or reject? That's the situation we're doing here.
Okay.
You can do a more complex process where you incorporate Bayesian experimental design or those design questions. But that's not what I was showing here.
Gotcha.
Yeah. Yeah.
All right, I'll ask it. It's all well and good to suggest that you can go to the decision maker and encode their values into your framework. And then once their values are encoded, you can say, given that you have this requirement for accuracy, this preference for cost, etc., then your right answer is this. Can you comment on the case where you go ahead and do that, and then the decision maker comes back to you and says, this was terrible, these weren't in fact my values at all. In fact, I wanted all of these other things, and they completely change everything out from under you. How can you, what can you comment on a situation like that?
When they're changing what from under you? Sorry.
Well, for example, you had to encode a value like a utility.
Yeah.
Right? And then you had to say, with your sigmoid sort of link function, you
Yeah.
were saying, here, I'm going to accept the something that barely passes or just barely doesn't pass has some positive utility. You've elicited some utility out
Yeah.
of some decision maker to
Yep.
code in theory.
Mhm.
The point that I'm trying to make is that often those values are very fluid.
Yeah.
And so how do you address a situation like that? Can you assign an uncertainty to the values of the decision maker?
I don't know. Yeah, because there's a level of subjectivity here, right? It's utility. Yeah.
I would say that as part of your elicitation of utility, you have to give someone a chance to play with things and say, oh, actually, no, I don't like that. And then their true utility functions can come to light.
Actually, very much like that answer.
Oh, good.
Let's thank our speaker.